We've already looked at how we can use a definite integral in terms of linear motion, and in particular finding the position of an object, knowing its velocity, and using the definite integral of the velocity to figure out how much that object's position has changed. We're going to apply the definite integral in a slightly different way, although it's the same idea, same basic idea, and that is using the integral as an accumulator, or adding up very small changes in something. In this case, we're going to be looking at a physical term called work, and work is essentially tells us how much force is put into an object over a period of time to move that object in the direction of the force. So work done by a force is defined as the force times the distance that the object moves in the direction of that force. When the force is constant, we have a very simple formula here where work is equal to force times distance, and this formula is very easy to use. However, most of the time the force is not going to be constant, it's actually going to be changing depending on where the object is. In those cases, we're going to have to use an integral. You can see in this integral formula here we have force times distance built in, where x right here is the distance. However, in this case, the distance is a differential, so we're talking about very small distances. We're going to use this integral here to add up the force times these very small distances and get work done over these small distances added up over a period of time, or over a particular distance, in this case from x equals a to x equals b. Units on work are a little bit different than other units that we've seen. In the United States, the customary units are usually foot-pounds, and 1 foot-pound is the amount of work that it takes to move 1 pound, 1 foot, in the direction of the force. In the metric system, typically we see Newton meters. Newton meters is the amount of work that it takes to move 1 kilogram, 1 meter. And you can see a lot of different units in terms of work depending on what kind of units are put into the problem. Let's take a look at an example of where we would have a variable force. A good example of that is stretching out a spring. It takes very little force to start stretching a spring, but as it gets stretched out more and more, the more force it's going to take to stretch it. In fact, we have something called Hooke's law that looks like this: force equals k times x, where k is a force constant for any particular spring, and x is the distance the string is stretched beyond its natural length. So in this particular example, we have a spring that is stretched 2 meters beyond its natural length, and it takes 10 newtons of force to do that. We want to know how much work it's going to take to stretch the spring twice that far, to 4 meters beyond its natural length. The first thing we'll have to do to figure out this amount of work is going to be to find the force constant for this particular spring. So we'll set up a formula here using the force that was given to us and the 2 meters here, using Hooke's law, and we can figure out then to find k, we can say 10 equals k times 2, and so for this particular spring, k is going to equal 5. Now, since for a spring the force required to stretch a spring a certain distance is given by this formula, we can take the integral of this, and we get the work as the integral of the force times the differential of x, or with respect to x. And since we want to know how much work it takes to stretch it to 4 meters beyond its natural length, we integrate this from 0 to 4. And we know for this particular spring that the force is going to be our force constant times x. Instead of f of x, we can replace that with 5x, and now it's just a matter of evaluating this definite integral. We take the antiderivative of 5x, which is 5 halves x squared. We evaluate that from 0 to 4, and so we get 5 halves times 4 squared minus 0 squared, and that's going to give us 40. Now, we also want to figure out what the units are going to be on this 40. like I said earlier, we might see a lot of different types of units on work. So in this particular case, let's try to figure out what the units are going to be on the 40 here. Let's see if they're one of the units that I've told you about already, or if they might be something different. Going back to our original formula that we used to find K, this 10 was measured in newtons and this 2 is measured in meters, so that means our K value is actually going to be newtons divided by meters. Looking at this integral right here, this K value, this 5, is going to be newtons divided by meters. Our X value right here is going to be meters, and our differential here is also measured in meters. So when we multiply all of these together, we have newtons divided by meters, times, and we end up with newtons times meters, which is, in fact, one of the types of units that I mentioned in the previous slide. We're going to see as we move on here that there are a lot of different ways that the definite integral can be applied, and at first glance they all seem very different, but they all have the same basic idea, and that is we're taking very small differences using this differential here and adding them up. So what we're doing here is we're using this integral, this definite integral, as an accumulator, adding up very, very small things and figuring out how much something changes over a period of time. So we have a rate of change multiplied by a distance here, and that's giving us work. So these integrals, these definite integrals, are giving us a way of adding up what's happening over a period of time, and the most important thing is it allows us to do that with a variable amount rather than a constant amount.